Alright everyone, this is the first video that you have that will help you with your last two assignments in Unit 3. And these are going to be 3 examples for 3.4b, solving radical equations. And as you can see from this first example, radical equations are equations we have to solve that have variables under the radical. And we see that right here, we have an x under the radical. So most likely you have an idea of what to do first when you have with a radical by itself. In order to get rid of the radical, the only thing you have to do here is square both sides. Since this is the square root, we're going to square the left, and when we do that we need to square the right. And in doing that, the square cancels out the square root. So we are left with 3x plus 1 is equal to 4 squared, which is 16. And we can see this is turned into a linear function, so we can just subtract 1. And we get 3x is equal to 15, so x is equal to 5. Now before we box in our answer, we need to remember that radical equations have domain issues. Remember, the things that are under a radical have to be greater than or equal to 0. So since we have a domain problem, we do need to check and make sure our answer works in the original equation. So what we need to do here is I'm going to rewrite what my original equation was. And we're just going to check our answer back into the original equation. That's the quickest way to do it for radical equations. You could just check and make sure 5 is in the domain, but you just want to make sure that it works. So when we have the square root of 3 times 5 plus 1, that gives me the square root of 16, and the square root of 16 is 4, and 4 equals 4. So that means x equals 5 is our solution. And that is example 1, when we have a radical by itself. All right. The second example we have is something that looks like this. We have 5 plus the square root of x plus 7 equals x. Now in this case, our radical is not by itself. So that is the first thing we need to do in order to solve this, because we cannot square this until this is the only thing on the left side of the equation. So we need to subtract 5, and we're going to have the square root of x plus 7 is equal to x minus 5. And we can see this is already looking a little bit different, because we have, not only do we have an x under the radical, but we also have an x on the right side of the equation. So the first thing we need to do now is square to get rid of the radical. And now notice what that looks like when I square the left and the right. If you square this whole binomial, remember, algebraically we're going to need to FOIL here. So my square cancels out the square root, and I have x plus 7 is equal to x squared minus 10x plus 25. Now again, this didn't reduce to a linear equation like my first example. Now I have something that looks like a quadratic equation. So I need to put it in standard form. I'm going to subtract x and subtract 7. We'll have x squared minus 11x, and 25 minus 7 is 18. And Now we have something there that looks like a quadratic in standard form, and I'm just going to double check everything, look at it one more time. And now since a is equal to 1, I'm going to factor to solve. So I have factors of 18 that add up to negative 11, and that would be negative 2 and negative 9. So my answers would be 2 and positive 9. But again, because of our domain issues, we need to check this. Now when we check it, notice we have 2 places to plug in x for. So over here I'll do it. We've got 5 plus the square root of 2 plus 7 equals 2. So we get 5 plus the square root of 9, and the square root of 9 is 3. So we can see there that this is not true. So x equals 2 is not a solution. It's actually called an extraneous solution. Well, let's check and see if 9 will work. So if I plug in 9, 9 plus 7 is 16, and we see that 5 plus 4 is equal to 9. So that is true. So 9 is our only solution for this equation. All right, so those are the main 2 types of examples you're going to see, and you just need to remember that if there's a variable on the right, you're going to have to square this binomial, which is going to make it look like a quadratic. All right, and remember, when you run into these in your homework, if you need to come back and look at the video again, make sure you use this as a resource. I'm going to show you one more example of radical equations. And this is a little different because now we've got 2 radical expressions. We have the square root of x minus 3 plus the square root of x plus 5 is equal to 4. So normally in our previous example, what we'd want to do is isolate a radical, but in this case we have 2. So what we have to do here is isolate one of the radicals. All right, we're going to have a little bit more algebra here. So when I do that, I'm going to subtract this over, and I'm going to get rid of this radical here first. So I'm going to square the left, which means I have to square the right. And my root cancels out here, so I have x minus 3. And this is where it gets kind of interesting because I have to FOIL this binomial that also has a radical, okay? So I'm going to write this out a little bit more so you can read my steps. Okay, so we've got to do our first terms, which is 4 times 4, and that's 16. And then our outer terms, which is 4 times this radical expression. So I have negative 4 root x plus 5. And then I do my inners, which gives me the same thing, negative 4 root x plus 5. And then I have negative root x plus 5 times negative root x plus 5. Well, a radical times a radical actually makes it go away, right? So the 2 square roots, let me show you that. So the negative times the negative is a positive. And then I have root x plus 5 times itself, right? So that's actually that squared. So the square cancels out the root here. Now once we get this cleaned up a little bit, these are like terms, so I can add them. So that's negative 8 root x plus 5. And then I just have my x plus 5 here. We can see that this x is going to cancel out this x if we subtract them. So again, we need to clean it up a little bit more. So I have 16 plus 5 is 21. And now I'm at the point where I need to isolate the next radical. So I need to subtract 21. And divide by -8. So I have 3 is equal to root x plus 5, and at this point it looks similar to our first equation. So I square both sides. This cancels out the root and I get 9 equals x plus 5, so x is equal to 4. Again, you want to check, and if I put 4 in here, I get 4 minus 3, root 4 minus 3, and then root 4 plus 5 is equal to 4. So this is the square root of 1 plus the square root of 9. So that is 1 plus 3 is equal to 4. So that is true. So my solution is x is equal to 4. And that concludes our examples. That will help you with homework 3.4, radical equations. All right, this is section 9.8. And you can see this is just kind of some handwritten notes I have. I don't have much technology here at home. But you can go to section 9.8 in the notes and outlines in MyLabs Plus and print out the notes, and you'll already see them solved, but that might help kind of follow along here as I show you the examples. Before we start with our examples, I have to explain what we're doing. This is called partial fraction decomposition, and it's a really important algebraic skill to be able to take into Math 172 and into a calculus course. And what this is it's taking a rational function like we just explored in Unit 3 and breaking it up in these are called the partial fractions. And so if I were to, add these together using a common denominator, this would be my resulting function. Okay, so what we need to be able to do is to work backwards. Okay, now I know you're thinking, why do we need to work backwards? But when you get into integrals and calculus, to complete an integral, it makes it a lot easier when you're able to break it down into partial fractions. So that's one of the main reasons we use this algebraic skill. Now what we have right here is this is kind of how we start. This is not the whole process, but how we start is we need to make sure the denominator's factored. So we need to factor it if possible. And this is going to look kind of crazy, but this is kind of the definitions that we need to start with. And then it'll make sense when I set up our examples. So what we're going to do with each linear factor in the denominator, so a linear factor that looks like this, where p is a coefficient and q is a constant, and n just means it could have multiplicities. We need to write that as the sum of n partial fractions. Okay, or basically we're going to set up an equation for a linear factor like this. Similarly, with a quadratic factor that is irreducible, it cannot be factored anymore, we also need to write this as the sum of m partial fractions. So we set up the equation kind of like this with, notice up here we have a constant on the top, but in the numerator here we actually have a linear function. Okay, so we just have to kind of remember we take a step down with our numerator. So if we have a linear factor in the denominator, we put a constant variable in the numerator. And if we have a quadratic factor in the denominator, we need to have a equation for a linear function in the numerator. Okay, again, looks kind of crazy. Let's go ahead and start an example. Now these are going to be pretty long problems, so you have to have some endurance as we get through this. And none of the things we're going to do here in this example algebraically are new, but we're going to combine a lot of things we've learned this semester. All right, so let's do our first example here. We want to decompose into partial fractions. So here is our function. Rational function, 4x minus 13 over 2x squared plus x minus 6. First thing we need to do is factor the denominator. And we talked about this in Unit 2. But I'll remind you, remember I did the bottoms up method. I multiplied this over to my c and get negative 12. And then I factor like normal. So factors of negative 12 that add up to positive 1. That's going to give me a plus 4 and a negative 3. And then because this was our unconventional step, I multiplied by 2. I need to divide both of these by 2. Reduce, so that gives me x plus 2. And then I move this here bottoms up and get 2x minus 3. So I have 4x minus 13 over x plus 2 and 2x minus 3. Now as you can see with it factored, I'm going to box this in because we're kind of done with this. This was just factoring. Okay. Now, as you can see with what we've done here is we actually have two linear factors. Now, from the previous page, let me just flip back. When I have a linear factor in the denominator, I set it up with a constant in the numerator, as in partial fractions. So since I just have, this just has multiplicity 1, then I set up my partial fractions like this. I have x plus 2, and then I'm going to put a up here. That's the constant that goes up top. Plus, and then my next denominator, 2x minus 3. And then I need to put another constant. It's not going to be the same constant. It's going to be a different one. So I'm going to put b there for that constant. And that is how we set up our partial fraction. This is what we're solving for. This is what we want. We want to know what a is equal to, and we want to know what b is equal to. So now we have something we can solve though. This is what we just looked at in Unit 3. We have a rational equation. And remember the steps for this was, after the denominators are factored, we're multiplying through by an LCD. Well, we know our LCD is x plus 2 times 2x minus 3. It's supposed to be a 2 there. I know that's small. Let me kind of zoom in a bit. And then we make our appropriate cancellations. So I cross out my thing what I have here. So I have 4x minus 13. My x plus 2 cancels out. So I have a times 2x minus 3. And I have b times x plus 2. All right, so before I keep going, again, notice nothing new. This isn't new, we factored before. This is the main thing that is new, is setting up the partial fractions. Okay, once we've set it up, we just solve our rational equation. And now we keep going. So I need to distribute my a. So I have 2xa minus 3a plus xb plus 2b. Just hold on just a minute. I'm going to put my camera down and grab a red pen. So we can see this. Okay. All right, so now what we're going to do is we're going to set up a system, because basically we need to find out what A is and what B is. But notice my 4x has to equal 2xa plus xb, right? Those are the x terms. So I'm going to underline those in red. And then my constant, my 13, I'm going to make a squiggly line here. This has to equal negative 3a plus 2b, right? That's where they're coming from. These x terms are adding up to give us 4x, and these constants are adding up to give us 13. So we can actually set up a system with this. So I'm going to set up the system with my red numbers, and these are going to be my x terms. So this gives me 4 equals 2a plus b. Notice I did not write the x's. I don't need the x's because those are the variables in the equation. Okay, I'm interested in what a and b are. And then my constants are negative 13 is equal to negative 3a plus 2b. Okay, so I'm breaking that into a system. Now, if you'll remember, I'm actually going to orient this how we would normally write a system. We normally have 2a plus b equals 4, and negative 3a plus 2b is equal to negative 13. Now we can solve this using substitution or elimination. Actually, let's just go ahead and use this using substitution. I'm sorry, elimination, right? I can multiply, I have b as a lone variable, so I can multiply this system by negative 2. This gives me negative 4a minus 2b is equal to negative 8. And then I add these two together, and that's why it's called elimination, because those eliminate. I get negative 7a is equal to negative 21, so a is equal to 3. And I can go back here and substitute a in for this. So 2 times 3 plus b is equal to 4. 6 plus b is equal to 4. So b is equal to negative 2. Let me circle those. Now that's not our final answer. Now it seems like a long time since we looked at fractions, but those, if we scroll back up here, those are the a and b that we wanted for these partial fractions. So a is 3 over x plus 2, and b is negative 2 over 2x minus 3. And that would be my partial fraction decomposition. So I started with a rational function, and I wanted to break it up into two partial fractions. So you could check this, right, by finding a common denominator and multiplying 3 by 2x minus 3 and 2 by x plus 2. And we would obviously end up with 4x minus 13. Okay, so here's a picture of the whole process, and I'm going to post 2 other examples. Okay, but we set up our partial fractions. We solved the rational equation. We set up a system to find our a and b, and here we solved it algebraically, and we plugged in our answers back into our partial fraction. All right, let's try another one of these crazy examples. All right, decompose into partial fractions. All right, we can kind of view it as a puzzle. We're trying to break it up and see what our fractions would look like before this. If you notice in this one, our denominator is already factored for us, okay? We also need to notice that each factor, this factor is linear, and this factor is linear, but it does have a multiplicity too, okay? So that affects how we set up our partial fractions, okay? I'm gonna go ahead and do this here. We have 2x minus 1, and a constant goes on top. Remember, if it's linear, a constant goes on top. And let me flip back so we can see this. Remember, this is when it has a multiplicity n, it has to be the sum of n partial fractions, starting with a multiplicity of 1 and going up to 2. All right, so what that would look like here is we would have plus b over x minus 2, okay, with a multiplicity of 1. And then I need to include it again with its multiplicity of 2. Okay, and that's just going to give us the other term we need. And notice how it works out nicely, right? We kind of, we have an A, B, and C, and we kind of see that we have 3 terms here. All right, so now we solve this rational equation. Okay, so we multiply through by the LCD. I'm going to write this in a different color. So remember, we have 2x minus 1, and then we have x minus 2 squared, okay, because we have to, the LCD is basically going to be what's over here. Just because of space, you can notice I'm kind of writing it on top there. All right, so we see everything cancels out here, which is what we want. 2x minus 1 cancels out here. Notice only one of the x minus 2's cancel out, so I'm just going to cancel out that radical there. I'm sorry, not the radical, the exponent. And then my multiplicity cancels out there. Okay, so let's write what we have left. We have a times x minus 2 squared. We have b times 2x minus 1 times x minus 2. And we have c times 2x minus 1. All right, lots of algebra here. Okay, so I'm just going to kind of work through it efficiently. This is going to be squared here. Let me just go ahead and write it like this so we can go through and FOIL quickly. Okay, so I have a times, I'm going to FOIL this first, x squared minus 4x plus 4 plus b times 2x squared. And I have negative 4x and negative x is negative 5x plus 2. And then I need to distribute my a, b, and c to every term. So I have x squared a minus 4xa plus 4a plus 2x squared b minus 5xb plus 2b plus 2xc minus c. Phew. All right, so again, nothing too new here algebraically. Again, the only new part was really setting up our partial fractions. Then we're solving this rational equation, okay? Now, after we've solved, right, we can't really solve anymore here. We have to match up our x squared terms, our x terms, and our constant terms like we did before. We want to set up a system, okay? So I will underline the x squared terms here in red. And then I'll underline the x terms in blue. And then I'll circle the constants in red.